Welcome to the new era of video creation with Bayo Z8. This is our new series on AI teaching natural language processing. Today, we will discuss the part of speech tagging. Here are the contents. Part of speech, POS tagging, is one of the foundational tasks in natural language processing, NLP. It involves assigning each word in a sentence a label corresponding to its grammatical role. This could be noun, verb, adjective, adverb, etc. POS tagging is essential because it helps machines understand the syntactic structure of a sentence. For instance, in the sentence, "the cat sleeps," POS tagging would label "the" as a determiner, DT, cat as a noun, NN, and sleeps as a verb, VB. The goal of POS tagging is to identify the roles each word plays in the sentence to better understand its meaning and structure. It is used in a variety of applications, from machine translation to sentiment analysis and information extraction. POS tagging is essential for understanding how words relate to one another in a sentence. It enables machines to identify the syntactic structure, which is the foundation of sentence interpretation. By tagging words, we can identify relationships between nouns, verbs, and adjectives, making it easier to grasp the overall meaning of a sentence. For instance, POS tagging is critical for named entity recognition, NER, where identifying the category of a word, e.g., person, location, organization, depends on knowing whether it's a noun or a proper noun. Additionally, POS tagging is an important step in syntactic parsing, where the sentence's grammatical structure is analyzed, enabling deeper linguistic understanding. In machine translation, POS tagging helps resolve ambiguities, such as distinguishing between homonyms, which is crucial for accurate translation. POS tags represent the grammatical roles of words. The most common types include nouns, NN. These represent things, people, places, or ideas. For example, cat, dog, and freedom are all nouns. Nouns can be further categorized into singular, e.g., cat, and plural, e.g., cats. Verbs, VB. These represent actions or states. Examples include run, eat, is, and seem. Verbs can also be conjugated into various tenses, e.g., ran, eating, eats. Adjectives, JJ. These modify or describe nouns. For instance, in the phrase, the big dog, big is an adjective. Adverbs, RB. These modify or describe verbs, adjectives, or other adverbs. For example, in she runs quickly, quickly is an adverb modifying the verb runs. These are just a few examples, but POS tags encompass a variety of categories, including pronouns, determiners, conjunctions, prepositions, and interjections. POS tagging can be challenging due to several factors. Ambiguity of words. A single word can belong to different parts of speech depending on its context. For example, bank can be a noun, financial institution, or a verb, to bank on something. Disambiguating these cases requires understanding the word's context. Complex sentence structures. Sentences can be complex, containing nested clauses or indirect speech, making it difficult to accurately tag every word. For instance, in the sentence, I know that he is playing, know is a verb, but is playing should be tagged as a verb phrase. Cross-linguistic variability. Different languages have different syntactic rules, which can affect POS tagging. For example, in Chinese there is no explicit distinction between adjectives and adverbs, which requires specialized tokenization and tagging systems. Rare or unseen words. Encountering words that were not part of the training data, e.g., new words or domain-specific jargon, can complicate the tagging process. Handling such words requires techniques like morphological analysis, or using subword-level models. There are several approaches to POS tagging. Rule-based methods. These use predefined sets of linguistic rules to tag words based on their context. For example, a rule might specify that any word following a determiner, like a or the, is likely a noun. While rule-based systems can be highly accurate for specific tasks, they are inflexible and difficult to scale for large, diverse data sets. Statistical methods. These methods rely on probabilistic models, such as hidden Markov models, HMMs. These models are trained on large corpora of text, and they learn the likelihood of a word belonging to a specific POS category based on the surrounding words. Statistical methods can be more flexible than rule-based systems, but require large amounts of training data. Machine learning models, supervised learning techniques, such as decision trees, support vector machines, and neural networks, are also widely used for POS tagging. These models learn from labeled corpora, making them adaptable to new, unseen text. Hybrid approaches. Some systems combine rule-based and statistical methods to balance the advantages of both. For example, a rule-based system might first be applied, and then a machine learning model is used for cases that are harder to handle with rules. One popular statistical model for POS tagging is the hidden Markov model, HMM. An HMM is a probabilistic model that assumes the sentence has an underlying sequence of hidden states, the POS tags, which generate the observed words in the sentence. In HMM-based POS tagging, transition probabilities model the likelihood of moving from one POS tag to another. Omission probabilities model the likelihood of a word corresponding to a particular POS tag. HMMs are efficient for tagging large datasets and have been widely used in various NLP tasks, including POS tagging. They require a large labeled training corpus to accurately estimate these probabilities, and their performance can degrade if the corpus is insufficient. Neural networks, especially recurrent neural networks, RNNs, and more advanced variants like long short-term memory, LSTM, and gated recurrent units, GRU, have shown impressive results in POS tagging tasks. These models are well suited for sequential data because they can learn long-range dependencies between words in a sentence. In neural network-based POS tagging, word embeddings are used to represent words as dense vectors in high-dimensional space. These embeddings capture semantic relationships between words, enabling the model to better understand word meanings. LSTM GRU architectures handle long-term dependencies, which is essential for understanding the context in which a word appears. Neural networks often outperform traditional methods, especially in tasks with complex or large datasets, but they require significant computational resources and large labeled datasets for training. Evaluating POS tagging systems typically involves several metrics. Accuracy, the percentage of correctly tagged words in a dataset. It is the most common metric used to evaluate POS tagging systems. Precision. For a given POS tag, precision measures the proportion of times the tag was correctly assigned compared to all instances of that tag assigned by the system. Recall. Recall measures how well the system retrieves the correct POS tag for a given word in the dataset. A system with high recall will tag most instances of a POS tag correctly. F1 score. The F1 score is the harmonic mean of precision and recall, offering a balance between the two. It is useful when the dataset is imbalanced or when there is a need to account for both false positives and false negatives. POS tagging plays a key role in many NLP applications. Syntactic parsing. POS tags are used to build a sentence's grammatical structure, essential for understanding how words relate to one another. Named entity recognition, NER. Knowing whether a word is a noun or proper noun is crucial for identifying names of people, places, or organizations. Machine translation. POS tagging helps break down sentences into their components, making it easier to translate them accurately. For example, distinguishing between nouns and verbs in both source and target languages is key for translation. Speech recognition. POS tagging can assist in speech-to-text systems by identifying parts of speech and improving the interpretation of spoken language. While POS tagging has made significant progress, challenges remain. Ambiguity continues to be a key problem, especially in complex sentences where words can have multiple interpretations. For example, bark can be a noun, the sound a dog makes, or a verb, to peel a tree's outer layer. Additionally, multilingual POS tagging is a growing field. Different languages have unique syntactic rules, and building systems that can handle many languages efficiently is a challenge. For example, Chinese has no explicit word boundaries, which makes POS tagging particularly difficult. Cross-domain POS tagging, adapting POS taggers trained on one domain, e.g., news articles, to another, e.g., social media, is another challenge, as the language and structure can vary significantly between domains. Looking ahead, advancements in deep learning and transfer learning techniques may further enhance POS tagging systems, making them more accurate and adaptable to a wider range of languages and domains. In summary, part of speech, POS tagging, is crucial for understanding the grammatical structure of a sentence and forms the foundation for many advanced NLP tasks. We've discussed various methods for POS tagging, from rule-based systems to modern neural network approaches, each with its strengths and challenges. POS tagging is indispensable in areas like syntactic parsing, machine translation, and named entity recognition. But it also faces ongoing challenges with ambiguity, multilingualism, and domain-specific adaptation. As deep learning techniques evolve, we can expect further advancements in POS tagging that will improve accuracy and applicability across languages and domains.